Okay, on the bench today we have a SICK Uniden PC68 LTW. This is a 40-channel AM-only radio, but it does have weather channels. Really good little radios, basically exactly the same as a Cobra 25 LTD. Circuit's the same. Matter of fact, you can use the service manual for it. The only real difference there is the weather channel. It has this rather large weather channel board here, so the layout is a little bit different on stuff like that. And this also has a dynamic squelch control, but the main chassis and the circuitry is the same. The only real difference there is the part numbers for like your semiconductors and whatnot. They may use a different identifier in the Unidens. They all start with a Q. But other than that, yeah, so they don't have TR numbers like TR for transistor 1. They'll have Q1 in the radio like this. But, so the first thing you want to do, well, actually, I guess the first thing is, what's wrong with it? So the customer sent this radio in. It has no receive. So he said there's no sound coming out of the speaker, and he also noted that there's absolutely nothing showing on the signal meter. So I verified that, put a signal into it. Yep, it's deaf as a doornail. Absolutely nothing on the meter, nothing out of the speaker. Not a peep, even at full volume. So nothing's even bleeding through this thing. It's just dead. So I thought I'd show a little bit of troubleshooting on this. Now, I've done some troubleshooting videos on showing how you can use the old-time signal tracers, the old vacuum tube signal tracers. They're great. Another tool that you can use for troubleshooting is a spectrum analyzer. Now, most people are probably familiar with the spectrum analyzer. We've got one sitting right there. You'll see me using that most of the time for things like looking at it'll be hooked up to the sample port. Basically, so the coax cable comes out of the radio, I'll be transmitting, and what I'm looking at is adjacent channel splatters. So, I'm looking for things like occupied bandwidth, I'm looking for spurious emissions, I'm looking for stuff out in the second harmonics, all the harmonic energy, and we're trying to keep all that down and keep our signal very small and within the band limits for the frequency, and very clean. But you can also do troubleshooting with something like a spectrum analyzer. A spectrum analyzer looks at frequencies, or looks at amplitude in the frequency domain. So where an oscilloscope, when you're used to seeing fancy little squiggly lines on the oscilloscope, what you're looking at is frequency in the time domain. The spectrum analyzer looks at frequency in the amplitude domain. So you can set the frequency, so the one edge of the screen will be at one frequency. You can set the frequency on the other side of the screen to another frequency. Usually what you do is you just set a center frequency. So, if, let's say CB channel 27.205, channel 20, you'd set your center frequency to 27.205, and then you set a span, for how wide, how much of the frequency spectrum are you actually looking at. I've got this one currently set to 10 kilohertz wide, so it's only looking at 10 kilohertz worth of frequency spectrum. And I'll be changing the center frequency as I go through troubleshooting this. And all I'm using to use the spectrum analyzer for this is an oscilloscope probe. No, it's not an impedance match because the oscilloscope probe is not a 50 ohm probe. But I don't care. I'm not taking quantitative measurements. I don't need to take accurate measurements and take precise measurements of the level. I just need to see if there's a signal there. If the signal, when it goes through a circuit, does it get bigger? Mixer circuits, are they working? I just need to see if the circuits are working. I could honestly care less about the actual amplitude. And actually, a lot of times when you're doing measurements like this, tracing signals like that, you really don't care about a precise measurement. You just want to see if there is amplification in each stage or filtering. Now, I will tell you, the first thing you're going to want to do if you do want to use a spectrum analyzer for stuff like this, where you're going to be probing around in a live radio where there's lots of DC voltages, put a DC block on the input of your spectrum analyzer. Last thing you want to do is have it go up in smoke. You don't want to blow the front end out. They'll have a DC rating on the usually printed on the front of your spectrum analyzer. It'll tell you what the maximum DC voltage there is, but I always prefer to be better safe than sorry and I put what they call a DC block. So I have a Narda brand right there. It's that blue thing. It's permanently attached. I just leave it there all the time. But that's what that is, that little blue thing right there. It's actually a DC block, and that prevents DC voltages from getting into my spectrum analyzer and causing havoc and damage. So what we want to do is use that to look at the frequencies as they go through the mixer circuits and the filter circuits in this radio and see where they are and where they stop. So the most important thing to have when you're doing something like this, other than the test equipment. Now, for the only things we're going to be using here is a signal generator. So I'm using communications test set right there. So it's actually putting and I'm putting a huge signal into this radio at the moment. I'm putting in a minus 35 dBm. So we're talking a needle pegged over to the right type signal into the radio, modulated at 100%. AM modulation, 1 kilohertz audio tone. So it's a big booming signal, so it makes it very easy to trace through the circuits, because even at minus 35 dBm, that's still a tiny little signal in the in the grand scheme of things. So that's all we really need for test equipment. Spectrum or any type of signal generator, and we're going to be using a spectrum analyzer. And you don't have to use that. There's other ways of troubleshooting it. It's just this video I want to show using a spectrum analyzer to do this testing. The only other thing you really need is, of course, a service manual. Kind of hard to do diagnostic. I mean, you can eyeball it. If you work on radios long enough, you pretty much can look at a radio and you know where the receiver circuitry is. You can just see where the filters are, where your IF stages are. But yeah, you should always have your service manual. It's going to give you very important information like your IF frequencies, your intermediate frequencies. So in the case of this radio, this is a dual conversion radio. So it has 2 IF frequencies. The first IF is 10.695 megahertz, and the second IF, which is common on pretty much any CB radio made pretty much ever, is 455 kilohertz. So how does a radio actually receive? Now, I'm not going to get into the detector diode, demodulation or anything. We're mainly concerned with the mixer chain and how that signal, the 27.5 megahertz, gets converted down to smaller frequencies. So what happens in this radio is you have a PLL synthesizer. That's what your channel selector is controlling. In the case of this radio, when it's on channel 20, the PLL is outputting, or you have, your synthesizer circuit is outputting a, 16.51 megahertz signal. So the signal comes in on the antenna jack on channel 20 as 27.205 megahertz. That gets a little bit of amplification. There's some front-end amplification to raise the signal up, because you got to remember, normally it's hooked up to an antenna. It's a tiny little signal, so they boost it up a little bit, and it goes into the first mixer. The mixers in this radio, they're for the first and second mixers, are both FETs. At the first mixer, what it will do is it will mix that 27.205 coming in the antenna jack with the signal that's being created by the synthesizer circuit. And that will change every time you change the channel selector, because what we want to come out of the first mixer is the first IF frequency. We want it to always be 10.695 megahertz. So when you mix signals, you take two frequencies, doesn't matter what they are. You take 2 signals and mix them together, you're going to get sum and difference frequencies. So you add them together, you can subtract them, you'll get harmonics, you get all kinds of mixing products. But your big ones are going to be, like in this case, is going to be the synthesizer will put out a 10.651 megahertz signal. So actually, just let's do the math there. That's why there's a calculator sitting here on the bench. So if we take 27.205 and we want to subtract the frequency that the synthesizer circuit is going to be putting into the mixer, which is going to be 16.51 when you're on channel 20. And that frequency changes every time you change the channel selector, because you want to be tuning into different channels. So we will subtract 16.51 megahertz from 27.205, and we get, there's our magic 10.695 megahertz first IF. So let's do a little bit of tracing. Stop the jibber jabbering. Okay. So if we look at the schematic here, and actually you can see, I even wrote it down in here to make it a little bit simpler. If you look in the service manual, actually this is the description of it. You can see now they have the top end and a bottom, but if I wrote down the frequency, because I always like to work on radios at their center frequency that they operate at. So 27.205 would be channel 20. For transmit, it creates a 10.69 or 10 or bleh, I'll get it here eventually. 16.965 megahertz frequency in transmit, which we're not dealing with transmit. The radio transmit's fine. What we're concerned with is for receive, it's going to be generating that 16.51 megahertz. That's your VCO frequency, or the output of your synthesizer. Like I say, you can see that changes depending what channel you're on. So if we just, I'm never going to get this spectrum analyzer and everything in view, am I? That might work. Just kind of keep it off to the side here. Actually, this might be a new camera angle I might have to start using. Keeps the camera out of my way and lets me get in here and work. Don't need a calculator. So, we have our oscilloscope probe attached over there to the spectrum analyzer. And first thing we can take a look at is actually the signal coming in the antenna. So I'll change the center frequency to 27.205 megahertz. So that's our center frequency. And I can just sample that up here on the weather board, this little connector here, because the receive signal needs to be able to go through either the AM radio, or it needs to be able to come up here through the weather board. So that yellow wire actually goes down and attaches directly to the coax connector. So makes it very easy to probe right there. But you can see, if I attach the probe, you can see there's our 27.205 megahertz signal. And you can see how large the sidebands are. That's because I'm modulating it with 100%, or it's modulated 100%. So, we know we have signal into the radio. It's making it past the coax connector. Now the first place I want to look is, turn the radio here sideways a little bit. I don't know if you'll be able to see it or not. So, here is our first mixer. There's a little FET down here, little tiny guy right there. It's that little black speck. And then our second one is actually embedded in a blob of glue. That little yellow spot right there, it actually should be black, but it has some of that nasty corrosive glue on it in between these two cans right here. So that's where we're going to be doing most of our probing. So this is the first mixer. So we should see 27.205 coming into it. And actually, if we look at the schematic, somewhere in here I had the schematic for this. Oh, actually it's on the next page. And I had written down here, we're going to focus. Okay, so the signal comes in, antenna comes up through, and you can see I have written down here 10.695, because here's our first mixer, FET, and then right here is our second mixer. So you're going to be having a 10.695 megahertz signal is coming in from down here from the synthesizer circuit, comes up, and then our signal coming in from the antenna comes in here, and then the signal, once it gets mixed, the 10 point, in the case of channel 20, 10.651 frequency will be coming in here, mixes with our 27.205, we're going to get a modulated 10.695 megahertz output of the first mixer. That'll go through a 10.695 filter, and that's a little tiny guy right, let's see, I think he's right in there. It's right down in there. There's a little tiny ceramic filter in between these two cans right here. It'll come out of that filter, ends up going into the second mixer, and this is the one where we're going to be converting down to 455 kilohertz. So what that mixes in, we'll mix in our modulated 10.695 megahertz signal. We'll mix that with a 10.240 megahertz signal. Again, grab the calculator, do a little bit of math. So if we take a 10.695 megahertz signal and we subtract 10.24, we end up with 0.4 455 or 455 kilohertz, and that's where we get our 455 or second IF frequency out of there. That'll come out, and you'll see there's coupling transformers here. They're also doing some filtering, but it'll come out there and it'll go through another filter, and that's this little, again, kind of yellowish because it's a lot of glue right here, but come on camera, hocus pocus, focus. So that's this little black eyes, those little rectangular black boxes that pretty much any CB radio has. That's the 455 filter. So we have 27.205 coming in to the mixer. Okay, let's see. These are, I'm trying to think what's the pin out on these. I think these are drain source gate, if I remember right. So let's see, the gate should be that one, and we can see there's just a little bit of signal there, but we can measure it. It is measurable. So there's our 27.205, and then I want to measure the output of the first mixer. And actually, if we change the spectrum analyzer, what I'll do is I'll now change the center frequency to 16.51 megahertz, which is the signal that the synthesizer circuit is sending in to be mixed. So 16.51 megahertz. And if we have a look again down here, you can see there's a nice big peak. Now, the frequency is not perfectly centered because I've not done an alignment because the radio doesn't receive yet. But yeah, so it's off frequency a little bit. Remember, our span's only 10 kilohertz. But so there's our 10.695, and that's the signal that's going to get mixed with the signal coming in from this coax connector. Now, the output is going to be our 10.695. So again, we want to look at that now. So I'll change it to 10.695 megahertz. There's our center frequency, or that's our first IF frequency. And I want to be checking at the far left-hand pin, and there it is. Still, this is always a battle working around a camera. Okay, so there it is. There is our mixed frequency. So the mixer is working. We've taken a 27.205 megahertz frequency from the coax, from the signal generator. We've mixed that with the 16.51 megahertz being generated by the synthesizer circuit, and we generated a 10.695 megahertz signal. So we're good so far. Next thing I want to do is probe the output of that filter. So there's, you can see I'm in between these two cans. I'm actually pushing it into the lead where it goes down through the board, but for that 10.695 filter. So we can see we have output from the 10.695 filter. So far, so good. Now, we want to check at the second mixer. Is our signal actually making it into the second mixer? So we want to check. It's glue. Just touch it to the lead. So there we go. There's our 10.695. Is at the input of that FET, or the second mixer. We also want to check for 10.240 because that's our mixing frequency to down convert to 455 kilohertz. So we want to check and see if we have an input frequency of 10.240, which is the reference, the actual frequency of the reference oscillator in this. So 10.240 megahertz. And there we are. We can see we have again, frequency is not perfectly centered. It's a little bit off, about the same, what you'd expect, because like I say, it hasn't been aligned yet. But yeah, it's off frequency a little bit. So, but there's our 10.240 megahertz. So our input is good. Now, what we should see coming out of the second mixer, remember, that was the math we just did here. The 10.695 minus 10.240, we should have a 455 kilohertz signal coming out. We'll change 455 kilohertz and see what we have. And there we go. There is a 455 kilohertz, still AM modulated signal coming out. So basically everything in the front end, all of the mixer circuits, everything seems to be working fine. So what's next in the circuit? Well, after the second mixer, it goes to the 455 kilohertz filter. And that's going, and what these filters are doing is, just like a lot of these transformers, you're filtering out, because remember, when you mix a signal, you end up with, you're still going to have 10.240 coming out of this mixer. You're going to have 10.695 coming out. You're going to have 455. You're going to have multiples and subtractions of all of those frequencies. All those frequencies will mix with themselves, and you just end up with all kinds of... But the only thing you want is 455. So that's why we have filter circuits, to filter out all of those other frequencies. So the only thing you're left with is 455. And all of the other signals, they'll still be there, but they'll be greatly reduced in amplitude. They'll be down several dB. And the farther down, the better. But let's just check the 455 filter. Let's see if we have signal going into and out of it. So, let's see here. Where are we at? Right. So there's our signal into the 455 filter. Still looks fine. And output would be nothing. There's nothing there. Oh, be quiet. Not you, the spectrum analyzer. Yeah. So it would appear we have a bad 455 filter. So, let me turn it off, disconnect everything here. What I'll do is actually reach down here and fire up the desoldering iron. Let's do this on camera. So I need to turn around here. Give me a second. I'm going to turn around and grab a 455 filter to replace that one. Let's see. Crystal filters. That was... what style is that one? I can't remember what's one they use in these. What letter, which is the actual filter bandwidth. Let's see here. Okay, so we have a new filter. And we got all this blasted glue in this thing. Yes, they definitely love their glue. Always jokingly say you'd think they were launching these radios to the moon or to Mars. They tried to make them so vibration resistant with this glue. And let's get this little critter sucked out of here. About all of this glue at the moment. I'll do all this off camera. I just want to get this stuff that I won't be able to get out once I get the filter put back in. Give me a second to do a little bit of scraping and scratching here. Like I say, I'll worry about all the other glue once I get this thing receiving again. Okay. And we'll take our new filter. Just slightly bending over some of the leads. It doesn't fall out on me. And soldering iron's already on. Problem soldering at arm's reach here. I can't see what the heck I'm doing. That's why you'll usually never see me soldering anything on camera. I'm doing it with my arms outstretched. Can't see what the heck I'm doing. So, let's hook this back up. Power, antenna, and holy moly, look at that. Full meter. If we hook, let me make sure the volume's turned down here. We're going to get blown out of our seat otherwise. That's actually what this little clamp's holding, is the speaker wire, so they didn't short out against anything. Let me get a speaker plugged in. Well, even without the microphone plugged in, I can hear a signal. And bam, there it is. So let me reduce for starters, the modulation down to 30%. And let's set the RF level down to, let's say, minus 110. Yep, it's receiving. There's minus 110 dBm input. I'll just going to do a quick by ear alignment. So, there you go. Successful repair. That's all that was wrong with it. Bad 455 filter. So, there you go. That's how you can use a spectrum analyzer to very easily trace signals that you normally otherwise would not be able to trace because they are so small. That's the big advantage of an instrument like a spectrum analyzer when it comes to things like this, is it can measure tiny, tiny little signals, down below minus 100 dBm. Stuff that an oscilloscope is just absolutely never going to see. There's no scope I know of that can, measure, you'll be able to see that waveform. But with the spectrum analyzer, you can see it. The other big advantage is you can actually see if your mixer circuits are working properly. Do you have your two mixing signals coming in? The signal from the antenna, the signals being generated in the radio, and you can actually check the output. Do you have output from your mixers at the proper frequencies? It allows you to check things like filters, which is what ended up being bad in this radio. Bad 455 filter. So radio works now. All I need to do is remove some glue, do a transceiver alignment on it, and this critter will be ready to be put back into service. It'll actually have a little bit better receive, because actually the crystal filter that I stuck in this is a little bit, and actually I see it's crooked, so actually I need to, like I said, I hate doing soldering on camera. It's hard trying to get it perfect. Yeah, it's actually crooked, so I need to desolder that and push it back down in. But that filter that I stuck in there actually has a little bit narrower bandwidth than what would have come from the factory in one of these, so it'll actually quiet up the receiver a little bit better. But there you go. So like I say, all you need is a signal generator, a spectrum analyzer, service manual, and a dead radio, and that's basically the procedure for going through. Just track through with your spectrum analyzer, continually changing your center frequency. Now, I had the span, like I say, I never changed the span on that. It was at 10 kilohertz the entire time. Just change your center frequency, start out, check for your input, make sure you're getting signal into the radio, that it's getting amplified, check at the mixer, you've got your mixing frequencies, you've got output from your mixer stages, check at each of the filter stages. So, the little ceramic filter trap down in here, the little filter block right here. And if this was fine, I could have continued on through the circuit. There's nothing saying that the transformer here might have been burned up or something. Parts can go bad, and there's just, any of the amplifiers throughout that entire chain can go bad. But, a spectrum analyzer with an oscilloscope probe is a very handy tool for tracing signals like this. Like I say, the only thing I suggest is if you're going to do that, even though that spectrum analyzer, at least this spectrum analyzer, can safely handle the DC voltages in this radio, it's still a good idea. It's better safe than sorry. Put a DC block. I'll say it again. Put a DC block on your spectrum analyzer if you're going to do this. Because the last thing I want to hear is, Mike, I did what you said about using an oscilloscope probe, and I probed in a radio, and it blew my spectrum, my however many $1,000 spectrum analyzer up. You've been forewarned. DC block. So there you go. I hope this helps somebody out, and maybe for people that don't really know that much about radios and how do you get that huge signal that comes in from the antenna jack, how does it get converted down back to audio and vice versa? Basically what you're doing in transmit is the same thing, just in reverse. You're mixing frequencies, coming up with and modulating signals, but that's how mixers work. You're taking two frequencies and you're generating dozens. It probably, if you had spectrum analyzers that could measure down to the unimaginable levels, you could probably see hundreds of harmonics and mixing products in there. It's only the couple of them that are going to be, fairly, large. All the rest of them are going to be way down in the noise. But that's what a mixer does, and we take advantage of that in radio communications, that marvelous fact that we can mix two frequencies together and come up with other frequencies. So, we can take any frequency coming in off the antenna. With the synthesizer circuit in the radio, we can generate basically a kind of like a counterpoise frequency. But the whole point there is you can take any frequency in, generate any frequency with within the realms of a CB radio frequencies range, but create whatever frequency you need with the synthesizer circuit, and you always end up with, as long as you have your mixing frequency right, you'll always end up with that, in the case of this radio, your 10.695 megahertz first IF frequency. And then, same thing at the second stage, you'll end up with a 455 kilohertz. So there you go. I hope that helps somebody. Maybe somebody get a few handy tips. And if you have a spectrum analyzer, this will show you some of the handy things you can do with it. And it'll help speed up your troubleshooting process. So instead of having to go through I think the mixer is bad, and just being a parts replacer, you can actually be a troubleshooter. Because unfortunately, that's mainly what we seem to have nowadays, is parts replacers. You'll see radios that have had every transistor and FET replaced. Like on the input chain. They'll replace the RF amplifiers, all of the mixers, everything, till they finally get to the bad part. And they go, aha, I fixed it. Well, yeah, you fixed it by loading up a shotgun and just blasting, God knows how many parts at it until it started to work. Anybody could do that. Shoot, the owner could have done that. Replaced enough parts and it would finally work. The whole point of doing this is being able to do it efficiently, quickly, by actually troubleshooting. And that's the whole point of doing stuff like this, is troubleshooting. And like I say, the most important thing there is a lot of times the service manual is a great starting point. Circuit description, okay? A good service manual will have a circuit description, so it will tell you how the frequencies are mixed. You can see right here, it's telling you RF amplifying Q1s mixed with, and that was our first mixer, Q24, to the first intermediate frequency. All the info's in here. All you need to do is follow through with either a signal tracer, like those old school, like you'll occasionally see me using RF audio signal tracers, using an oscilloscope, depending what type of circuit you're working on, or a spectrum analyzer. But the info's here. You just need to trace through. Just follow Q1, Q24. Just follow through those circuits with your probe, and, of course, tracing through on the schematic, tracing your signal through, and seeing where it disappears. So, there you go. Like I say, I hope that helps. So, enjoy.